Hello students, welcome to today's session. Last time we were discussing about tokens and we covered keyword kind of tokens and identifier kind of tokens. Today we'll be looking at literal category of tokens. And before we start literals, I would like to bring your attention to the name of this chapter. The name of the chapter is Values and Data Types. So values or data, they are the same thing, okay? A data represents some value. So values and data, both of them are the same thing. And the word literal is actually referring to values. Okay, so literal means values, and since values and data they are same, literal also means data. Okay, so in this category of token, that is literal kind of token, we'll see different literals along with their different types. Okay, we are going to study the literals and their different types. Okay, so literals and literals type, or values and value types, or values and data types, all these terms mean the same thing. So let's start. So there are four main categories of literals: numeric, non-numeric, Boolean, and null. Numeric has further subdivisions: integer, and within numeric you have integer literal and real literal. Within non-numeric literal you have character literal and string literal. Now let us look at each of them, starting with the numeric kind. So numeric literals are values that may consist of digits from 0 to 9. It can consist of a decimal point, and it can contain the plus symbol or the minus symbol. Okay, so a numeric literal can consist of digits from 0 to 9, a decimal point, plus sign, and minus sign. Now the integer kind of literals, they will contain only digits. Okay, they will contain only digits along with a positive sign or a negative sign, but it will never contain decimal point. Okay, so integer literal will consist of digits from 0 to 9, plus sign or the negative sign, but it will not contain the decimal point. This is the meaning of integer literal. So look at this example here, 1455. It contains the digits. Okay, and we don't have any symbol here. If there is no symbol present before the number, it is considered to be a positive number. Okay, or you can explicitly mention positive sign before the number. It will mean the same thing. Okay, so even if you do not write plus sign, it will by default take it as positive. And the last example shows a negative number which has got a negative sign here before the number. Okay, so integer kind of literal will have any one of these forms. Okay, do not confuse this sign with positive. Okay, it's not a positive sign, it is just a bullet point. It's just a bullet point. It's not a positive or negative sign. The sign is here. This is the sign. This is the sign. Okay, and this does not contain any sign. Okay, so this is how integer literals look like. And there are two more points. You cannot have a space. You cannot have a space in between the numbers, and you cannot have commas either. Okay, so no commas and space are allowed. So if you look at an example, so we have got our class here and the spelling of literals is wrong. So I have corrected it, but even if it was wrong, it would have still compiled, because last time we discussed about identifiers, and identifiers can be any name of your choice. Okay, so our class is created and we need to create a function, because every Java program should consist of at least one class and every class should contain at least one function. Okay, because our Java statements, they live inside the function and the function itself lives inside the class. Okay, so let us create the function. Okay, this is creating a problem because I have changed the class name again. So let me just close this. Okay, so let us create the function. Now let us create an integer kind of variable. So the name of the variable is num. Inside this num, I can store integer numbers because the type of num is defined as int. So I can store integer literals here. So we can store something like 189. Okay, and if we compile this, the code will run, okay, without any problem, no syntax error. I can write here plus 189. That's not a problem. This will also compile, as you can see, no syntax error. And finally, I can assign a negative number, a negative sign to it, and that is also fine. Okay, it will still compile. Now if I try to put a space, okay, let's say 18 space 9. Okay, so notice the space after 18 I've got a space here. If I compile this, it will not compile because this is not a valid literal. Okay, similarly, I cannot have a comma in between the numbers, in between the digits. I cannot have comma, so this will also not compile. Okay, so errors found. So remove the comma, compile it, and it will compile. So I hope this point is clear about integer literals. Okay, so within the numeric literals we have seen integer literals, and now let us see real literals. Okay, the second category of numeric literals. So real literals are those literals which have the decimal point, okay, and all other rules which applied to the first category of integer literals, it will still apply to real literals as well. The only difference is that it will have a decimal point. Okay, so real literals are also known as floating point literals, and they have a decimal point, and they can be written in two forms, either in fractional form or in the exponential form. Okay, so all these examples here are the fractional form of real literals. Okay, they are in the form of fraction. Okay, so the first one is 42.33. okay, you can see the point here. So 42.33, this one is minus 23.90, this one is plus 2334.05, this one is 7348.009, and this one is 0.001729. All these are examples of fractional literals, fractional real literals. Okay, so what are the points you must remember regarding real literals? It must have a decimal point. Okay, because if you do not give a decimal point, it will not be a real literal anymore, it will be a integer literal. Okay, so that is why a decimal point is necessary. Okay, second rule is that it must have at least one digit after the decimal point, that is you cannot write 2355 point. Okay, third point is that you must have at least one digit before the decimal point. Fourth one is two decimal points are not allowed, and the third one is comma is not allowed. So let us see the practical example for all these points here. Now, integer literals are represented by which data type? They are represented by the int data type. Okay, but real literals can be represented as float, as a float type of data, or a double type of data. Okay, So you can use either a float type or double type. For the moment, let's use double, and we'll see float and double in detail when we discuss data types. For the moment, we'll just create a double variable, okay, and let us name it as num2. So double num2, okay, and num2 will store our decimal value. So what was the first point? The first point was it must have a decimal point. That is, if I write 156, even if you write 156, okay, and you compile it, it will not cause any. Oh, I missed a semicolon here. Okay, if you compile it, it will compile, okay, but then you can ask me that what is this first point then? It must have a decimal point, but as you can see, I don't have the decimal point here. So what is going on here? Well, the thing is, if you do not write a decimal point here, the compiler will insert a decimal point for us, okay? Although we have just written a number without a decimal point, but internally it will be converted into a decimal numbers, okay, something like this, 156.0, okay? So internally 0.0 will be added, and then it will be stored in the memory. That is why we are not getting any error, okay? So that is what is meant by this statement here. It must have a decimal point. Next point is it must have at least one digit after the decimal point, and it must have at least one digit before the decimal point. Okay, so let us say I remove this 0 here, and now it is just 156 dot, okay? So this will result in an error, as you can see. So let us say we have got some number here, 56 point. See, the rule is that you should have at least one digit after the decimal point. But if I compile this, it will still compile, because again, Java has helped us by providing a 0. If it sees that there is no digit after that decimal point, it will add a 0 for us, okay, and it will make the number as valid. Similarly, if we do not write a digit before the decimal point, it will again compile, but internally it has made it as 0.3, okay, that is why it is not resulting in an error, okay. Otherwise, the rule is that after the decimal point and before the decimal point, there should be at least one digit. And the next rule is 2 decimal points are not allowed, and of course comma is not allowed, okay. So you cannot have 2 decimal points. So if I write 0.3.1, this is not a valid literal. This is not a valid real literal, okay. So as you can see, we have got an error here because of the extra decimal point. So we have seen the fractional form. Now let us see the exponential form. So in the exponential form of real literal, it consists of 2 components, mantissa and exponent. and it is used for writing numbers in the scientific notation. And if you don't know what scientific notation is, let me explain you. So the number which you can see here, this is known as the scientific notation. This number here. So both these examples are in the form of notation. So this part here is known as the mantissa, and this part here is known as the exponent. Similarly, in the second number, this part is known as mantissa and this part is known as exponent. Okay, so what is a number in the scientific notation? It must have a mantissa multiplied by 10 to the power of some exponent. Okay, so this is how scientific notation is written for a number. Let's take two examples. In the first example, I've got this number here, and in this example you can see that I don't have decimal point. You know that if I write any number, let's take 56, so this 56 is same as 56.0. Similarly, if I take 78, this 78 is same as 78.0. So in all numbers we have a decimal point present at the end if we don't have it explicitly mentioned. So the decimal point is here, and we want it to convert it into this form. That means what? I have to take the decimal point from here till here. Okay, and how this can be done? So I have to move the decimal places towards the left. Let us count how many times we have to move. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we have to move the decimal point 10 times towards the left. And why did we choose this location? Why should the decimal point come here? It is because that in the scientific notation of numbers, there must be only one digit present to the left of the decimal point. In the second example also you can see I've just got one digit to the left of the decimal point. Okay, so the most important rule while writing numbers in the scientific notation is that you must have only one digit to the left of the decimal point. So coming back to our example, our number has become 1.234. 1.234 and followed by 7 zeros, right? So this is the state of the number after we have moved the decimal point 10 times towards the left. But we cannot change the value of the number. Okay, that is why we need to multiply this number by 10 to the power of 10. Why to the power of 10? Because we moved the decimal point 10 times towards the left. That means what? If I multiply this number here by 10 to the power of 10, we will get the original number, and hence there is no difference of value between the number present here and the number given here. Both the numbers are exactly same. So this was the first example. Let us have a look at the second example. In the second example, this is the number and we want it to write it in the scientific notation. That means what? In this case we have to move the decimal point how many times? Let's count it. 1, 2, 3, 4, 5. We have moved the decimal point 5 times towards the right. So the number is 1.497. And since we cannot change the value of the number, we have multiplied it by 10 to the power of minus 5. Why is it minus 5? Because in this case we have moved the decimal point towards the right, but in the previous example our decimal point was moving towards the left. So whenever you move towards the left, you have to multiply it by 10 to the power of some positive number, and whenever you move the decimal point towards the right, you have to multiply it by 10 to the power of some negative number. So I hope scientific notation is clear. And now you can understand what is mantissa and what is exponent. So let's take this example given in the book 67.E7. Okay. So whatever number is present towards the right of the letter E, that represents the exponent part, and whatever number is present before the decimal point is represented by the number before the decimal point. So let's write a code for it and see what is the output. So if I write 67.E7, and E can be either capital or small, it does not matter. So 67.E7. So what do you think the output for this will be? So the question is, what is the output of this number here, 67.E7? Since it's a very big number, you'll have the output in the form of the exponential form, but it will not be 67.E7. It will be 6.7 6.7 E8. Okay, so 8 is the exponent and 6.7 is the mantissa. So why did it become 8? It was 7, isn't it? So if you see, the number here was 7. After E we had written 7, but now in the output it has become 8. What is the reason for this? The reason is because scientific notation can have only one digit to the left of the decimal point. So that is why 67 became 6.7, and we have moved the decimal point towards the left. If we have moved the decimal place towards the left, that means what? You have to multiply it by 10 to the power of what? Since we have moved 1 times towards the left, that means we'll multiply it by 10 to the power of 1, and we already have got 10 to the power of 7 here, so it will finally become 10 to the power of 8. Okay, and this is the reason why the output is showing as 6.7 into 10 to the power of 8. Let's take the second example from the book. So minus 350 E4. The number is minus 350 E4. So let's see the output for this. So as you can see, the output for this is minus 3, 5 followed by 5 zeros. That is 3 lakh. Sorry, it's 35 lakhs, minus 35 lakhs point 0. So our number given is minus 350 E4. E4 means what? Into 10 to the power of 4. So if I multiply the number here by 10 to the power of 4, the number will be 350 followed by 4 zeros. Let's take the third example, 5.600E32. 5.600E32. If I compile this and let's execute, the output will be the same number. Okay. Since the number is very big, it is showing in the scientific notation 5.6E32. That is 5.6 into 10 to the power of 32. So I hope the exponential form of real literals is clear.